Yeah, my name is Jonathan Birkel, and today I'm going to be talking about extreme heat, kind of as it pertains in particular to public health. And so I am a second-year master's student in the Land and Atmospheric Science program, and my advisor is Dr. Tracy Twine. And then I should acknowledge my other main collaborators on this work are Stefan Leese, who's also in our department and has done a lot of the downscaling climate model work that I'll be going over a bit, and also Larry Kalkstein, who is a longtime member of the faculty at the University of Miami in Florida, who has done a lot of work over the years on the relationships between heat and health. So, like I said, public health is kind of the perspective that I'm approaching extreme heat from in this work. And it's kind of an under-recognized fact often, but heat is the leading weather-related cause of death in the United States. But even though there's some pretty well-established links between heat and health, the mortality and morbidity that result from heat events are often underreported. And that's just because of the difficulty in attributing them to the heat on a case-by-case basis, when oftentimes, rather than something obvious like a heat stroke, you see an uptick in heart failures or respiratory failures or things like that. So instead of looking case by case, you can get a clearer picture of the relationship if you look at all-cause mortality and how it exceeds the baseline during these kinds of heat events. And one thing that's important to note is that urban populations are particularly susceptible to the health risks from heat, and so they're kind of central to a lot of discussions on this topic. And within urban populations, it's particularly the elderly demographics who tend to be most impacted by these events. And you also see a lot of racial disparities where neighborhoods with a history of redlining tend to experience the most heat stress. And there's a lot of reasons for that we don't really have time to go into, but that's unfortunately a problem all over the country. But anyway, there are specific categories of air masses that are particularly linked to summer excess mortality, and so that's kind of the focus of my work. So thinking about extreme heat, Minnesota might seem like a bit of a counterintuitive place to be worried about a thing like that, where you might think of Minnesota and picture something like this. This is my neighborhood just a few weeks ago. But in fact, a place with a high variability climate like Minnesota is kind of what makes it more of a concern in some ways than places that are consistently hot, because not only do we have a lot of variability over the whole seasonal cycle, but also we do intra-seasonally. So within the span of a summer, it's not going to stay as consistently hot. And so that limits how much people are able to acclimatize to the heat. And so a big question then is, how is climate change going to influence all this? And these figures on the right are examples of some outputs from the downscaled climate models that we have for the Minnesota region. And so we've got a simulated version of the late 20th century, as well as moderate emissions in the mid-21st century, and then both moderate and high emissions, that's RCP 4.5 and RCP 8.5 respectively, that, as you can see, by late in the century, those two scenarios diverge quite a bit more in terms of how many of those really hot days we're likely to expect to see. But it's not just how hot it gets during the daytime that matters with these events. We also care a lot about how much it cools off at night, because nighttime cooling after a hot day provides a lot of relief, physiologically speaking. And so if we look at Minneapolis during the summer over the last 75 years, we can see that those daily highs have not really changed all that much, but that there has been a statistically significant increase in those daily lows, and that results in a narrowing of the diurnal temperature range. And you might think of that, you might take a look at that and think that might be a symptom of climate change that's already becoming visible, but it's more likely that that just has to do with the urban heat island as well. And hotter nights are what leave cities more vulnerable, because if you can see these figures of the summertime urban heat island, it's a bigger urban-rural distinction at nighttime than during the daytime. And so urban residents don't have that cooling relief to the same degree that nearby rural populations might. And as an example of this, we can see that the Minneapolis-St. Paul urban heat island is strengthening compared to how it was 75 years ago, or if you compare the diurnal temperature ranges between the Minneapolis airport observations, which is fairly central to the metro area, as compared with Jordan to the southwest, which is really kind of right on the edge of the urban heat island's influence. You can see that the diurnal range has decreased more in that urban central area, and that's a pretty common phenomena to see if you look at other metro areas over the same period of record. But even just looking at temperature, if you're including minimum and maximum temperatures, that's still only giving you part of the story, because temperature is just one element of weather that the human body experiences. We tend to experience weather more as a whole ensemble of lots of elements. And so there's methodologies that we can do to kind of account for that and help us get a better sense of how things are changing in a way that's more meaningful to health outcomes. So what we can do is we can categorize different types of air masses that pass over a region, and those tend to be associated with a source region. So some, as you can see, form over the ocean, and some form over continents at different latitudes, and that influences their temperature and moisture characteristics. But it's worth noting there's also moderate types, which takes into account that these air masses' character can change as they pass over the landscape. And so there's lots of different ways that you can classify air masses, but the one that we're using is called the spatial synoptic classification, which has had a couple different versions over the last few decades of its development. But one thing that's important to note is that it's a hybrid procedure, so it's not fully manual in terms of assigning air mass types to days, which means that it's not quite as subjective as it would be that way, but it's also not a fully automated system, because systems that are completely algorithm based and not subjective at all tend to have a little less spatial continuity between adjacent weather stations. So basically how this works is there's some manual selection that goes into picking seed days, which basically exemplify like the typical characteristics that an air mass would have at that specific location at a particular point in the year. So you look for a good example of each air mass type kind of in 4 2-week windows throughout the year, and then from there the algorithm kind of fills in the gaps and assigns an air mass type to every day through the whole year. And so what this allows us to do is compare how trends may not look uniform across all air mass types over time. So looking on the left here, empty or moist tropical days are some of the more hot and moist that we see, and those have had a small but statistically significant increase in their nighttime temperatures, whereas the hot and dry or DT days have not. This is specifically summer temperatures from June 1st through September 15th, by the way. But yeah, just an example, trends are not uniform, and so it helps to break things down a bit more like this. And also worth noting, the DT days, the hot and dry, are not all that common. You tend to see less than 10 of them per summer, whereas the MT days are more common and increasing in frequency relative to 75 years ago. And that increase is mostly at the expense of the cooler and drier DP or dry polar air mass types. So that's one thing to note when you're looking at the shifting climate in a region, is the shifting dominance of certain air masses over others. And so how does this all translate to health outcomes then, which is really kind of why we care about this, at least in the case of this type of research that I'm involved in. So we can see that there's particular air mass types that are associated with higher mortality, where on this figure on the left, 0 represents the baseline, and that either if you look at total mortality or specifically among population 65 and over, you can see that the DT and the MT plus are, as they typically are, the most oppressive air mass types. And I should note that MT plus is a subset of MT, where your apparent temperature is greater than a standard deviation over like the seed day kind of typical conditions. So it basically just means it's a more extreme version of it, and you have plus versions of other air mass types as well. but this is kind of the main one that we care about in this context. So it's also worth noting the differences between total and 65 plus mortality, how on the DT, those tend to be the hottest days of all, where you have less moisture to keep the temperature in check. And so that's more likely to impact people who are spending more time outdoors, especially if they're working in an outdoor setting. Whereas MT plus are the really hot, but particularly oppressively humid days, where that's more likely to affect older people who are staying inside, particularly if they don't have air conditioning. So thinking forward about health outcomes in the future, that's something that we kind of want to have a sense of how cities can prepare for these things. And we can look more basically at trends in summer minimum temperature just across all air masses and see that particularly in a high emissions scenario by late in the 21st century, that's this bottom right figure, those nights are going to get a lot warmer and we'll have a lot less of that nighttime cooling relief. But as I said, the trends across all air masses are not uniform, so we want to break things down further. And so in order to do that, this is where the downscaling kind of can feed into the daily synoptic classifications, and those two methodologies can build off of each other. So the actual downscaling work all kind of happened before I became involved, but we have 8 general circulation models where the resolution spatially is on the order of a couple degrees of latitude or longitude. And then we use a WRF model, which is a weather research and forecasting, to downscale it to about a roughly 10-kilometer grid. And then to kind of imitate the methodology of the SSC, we're kind of treating specific grid cells as though they are weather stations and pulling the variables we need out of those. And that's kind of the ongoing challenge, is just getting all of those in the right format that can be usable, especially if the model didn't originally output all of those for its original uses. But we want to look at the frequency of oppressive air mass types going forward into the future, and if more of them will occur in consecutive days, or what point in the summer will that occur, because that has implications for acclimatization and also just how will the character of each of these air masses change. And the idea here is to promote ways that cities can help mitigate these risks as they go forward, either through increasing the urban albedo of surfaces like roofs or pavements, or just having more tree cover. But to really understand how best to mitigate these risks, the cities need to understand the risks going forward on a more local level. And so that's what we're hoping to inform here. So thanks everybody. And now I'd like to open it up to questions.
Great, thanks so much. So we've got about 2 minutes for a question. And we actually have one in the chat from Lindsay. Could the increase in MT and MT plus days related to more hurricanes / post-tropical depressions happening and sometimes reaching the Midwest? Maybe I didn't read that.
Yes, yeah, that's a great question. And typically that is how we get those kinds of days here, is if you have the Bermuda High is one example. It's like a high pressure system that kind of forms over the tropical Atlantic. And if that's a strong enough system as it can develop into being by a certain point in the summer, then that's really where we get those like really hot and humid conditions that can make it all the way up here. And so that's one thing that I'm not an expert on, but like the seasonality of those kinds of events is something that may shift. And so we want to keep that in mind, because like hotter and more humid conditions that are more oppressive make a bigger difference, especially if it's earlier in the summer and people have had less time to become acclimatized.
Yeah, great. We got one more question in the chat here from Jabari. Do you have any sense for how small scale geographic variations can impact risk? For example, does downtown have higher risk than a more residential neighborhood? And is there fine enough resolution data to resolve that?
Yeah, that's a great question. And the downscaled models that I'm working with are, it's like a 8 to 10 kilometer resolution. So that's not really great enough to characterize like urban heat islands on a neighborhood scale, like in a projecting into the future sense. But that is a project that is being done in a lot of places, and you can see like differences in thermal characteristics between lots of neighborhoods within smaller portions of an urban area, and that's how we can really tend to get a better sense of some of those, racial disparities and things like that. If you look at formerly red line neighborhoods that tend to be the hottest, and based on things like tree cover or quality of infrastructure or construction materials, or also just whether people have air conditioning is a factor. But it's kind of the net result of a lot of different factors that don't have the prettiest history.
Yeah, great. Well, yeah, we do have a few more questions in the chat, but unfortunately we are short on time. So if you do want to reach out to Jonathan directly to chat more about this really interesting research, we definitely recommend that. But we do need to sort of shift over to our next talk. So thanks again for chatting with us about this, and definitely really exciting and interesting stuff to be thinking about, especially, since we're all, or most of us are in the Twin Cities. This definitely is relevant to a lot of us.
Well, thank you so much for listening.
Yeah, great.